The term wheel and axle is pretty self-explanatory. It's just a wheel attached to some shaft or some axle. Let's go ahead and write out a definition for ourselves. So a wheel and axle. It is simply a rotating wheel, and I'm going to put wheel in quotation marks, that is attached to some drive shaft, or otherwise known as an axle, and I'm going to put axle in quotation marks as well. And then an important point to add about a wheel and axle is the effort is applied to the wheel. And again, I'm going to put wheel in quotations, to overcome the resistance of the axle. And actually, let's go ahead and add quotations around axle as well. And we put wheel and axle in quotations for a very good reason. If you look here, the wheel doesn't always have to look like a wheel. So if we look here at this first example, we can see that this is a wheel clearly attached to some axle. We can look at the steering wheel. We know that we turn this wheel by applying some effort to it, and the resistance would be in the attached axle. And again, I'm turning this wheel to gain some advantage to turn some axle attached to the other end. But sometimes it doesn't look like a wheel. We still have this rotating quote-unquote wheel turning some axle, but it's not round like a wheel. It looks more like a rigid bar. It looks more like a lever. And that could be kind of confusing at first. So to explain what I mean, let's start by sketching out what a wheel and axle problem will actually look like. And so we'll start with just two circles. So we'll start with a big circle to represent the wheel, and then we'll draw a smaller circle on the inside to represent the axle. And then we can even label the bigger circle as our wheel and the smaller circle as our axle. And this is just a front view of that wheel and axle. And so to picture this, if you look down here at this valve or at this faucet, you'll see we've got the wheel, but we know behind this wheel of this valve, there is some axle coming out the other end. And so that's what this inner circle represents. It's something that you can't technically see from the front necessarily, but we know it's there behind it. And then I'm going to add a fulcrum to the center representing the turning point of both our wheel and our axle. We know that it'll turn around, both the wheel and the axle will turn around that fulcrum. And then I'm going to add an imaginary line to demonstrate where the force effort and the force resistance will be applied. And we know the force resistance will go right here at the inner circle along this line. So where this imaginary line meets our axle is where I will put our force resistance, and where the imaginary line meets our wheel is where I will put our force effort. And so basically what it ends up looking like is just a second-class lever with two circles around it, with the smaller circle representing the resistance and the bigger circle representing the effort. And we can even label this as the wheel as our distance effort, and we can label the axle as our distance resistance. And this becomes just a simple way to sketch out a wheel and axle without having to be an artist. And what you have to picture, what you have to see, is this force effort is going to go around the wheel. And so to look more like this in reality, where the force effort is going around our wheel and down the other end of our drive shaft, at the other end of our axle, we will have the force resistance fighting it. But essentially that's all a wheel and axle is some rotating effort trying to turn some attached axle. And so if you look at this example again, you can then see how this is a wheel and an axle. It will rotate around, turning the attached axle. And so another example of this would be this tire iron. So what do we use tire irons for? Well, on a wheel of a car, you will see lug nuts holding the wheel on. And to tighten or loosen those lug nuts, we need a huge amount of mechanical advantage, and that's where the tire iron comes in. We insert this hexagon right onto that lug nut, and then we grab it along this crossbar to apply your effort. And so we can say the force effort is here on the left side of this crossbar, but actually I'd have to grab it at both ends of this crossbar to rotate this axle, which would be attached to some lug nut, to either tighten it or loosen it. And so the force resistance is here at the other end of the shaft or axle. And this is what makes it technically a wheel and axle. Even though technically this crossbar does not really look like a wheel, in fact, it looks kind of like a lever at first glance, the fact that the resistance to overcome is in the attached axle, this rotating effort applied at this crossbar effectively becomes our wheel. And since we have a wheel and axle and we have its measurements, let's go ahead and calculate the mechanical advantage. And so we've got this 26-inch tire iron, which we'll insert on this 2-inch lug nut to twist it around with some effort force. And so we're given two distances, so we need to calculate the IMA. And remember, your IMA is your Imadeer equation. Your IMA equals your DE divided by your DR. And in this case, the distance effort would be one full rotation. Or in other words, your circumference of your outer circle. And so actually we can even rewrite distance effort as the circumference of our effort. And then E for effort. And we'll divide that by the axle circumference, which is the circumference resistance. And actually I forgot that little e here. And R for resistance. And remember, the formula for circumference is 2 pi r. Or another way to write it is diameter times pi, since 2 times your radius is your diameter, where this circle with a line through it is your diameter. And so then we can rewrite our Imadeer equation to be equal to 2 pi times the radius of our effort divided by 2 pi times the radius of our resistance, which would of course be equal to our circumference. Or we can rewrite this to say pi times the diameter of our effort divided by pi times the diameter of our resistance. And this might look familiar. This is something we've done before in our lever lessons. You'll notice that 2 over 2 cancels out and pi over pi cancels out. And so you're left with the radius effort divided by the radius resistance. And similarly, over here, pi cancels out and we're left with diameter over diameter. And so if this is true, then it means we could use any one of these three values to find our mechanical advantage. We could use circumference, radius, or diameter. And so let's go ahead and give that a try. Let's see what happens if we use our circumference to find our IMA. And so we'd say our IMA is equal to our distance effort, which would be our circumference effort. And so to figure this out, we need to use our handy-dandy calculator. And our formula for our circumference, we're given a diameter, so it's diameter times pi. Our effort is this 26 inches. That's where we're applying our effort. And so we'd say 26 times pi, which is 3.14. And we get a circumference effort of 81.64. And so on top, we would say 81.64 inches, and that would be the effort applied to our wheel, our outer effort. And we'll divide that by our distance resistance, which is this 2-inch lug nut that we're trying to turn. And so that's the diameter of the lug nut. So we'll say 2 times 3.14. And we get 6.28 inches. And we know that inches cancels out. And so to figure this out, let's pull our calculator back out. Let's say 81.64 divided by 6.28. And we get a IMA of 13. And then if we do the same thing for our radius, we are left with just the radius effort divided by the radius resistance. So let's calculate the IMA using our radiuses, or radii, I guess, would be the more correct way to say that. So we'll say IMA is equal to our radius effort divided by our radius resistance. Well, the radius is just going to be half of our diameter. Well, 26 divided by 2, hopefully you don't need a calculator for that. That would just be 13 inches. And the radius resistance would be half of our 2-inch diameter lug nut, which would just be 1 inch. And of course, inches cancels out, and 13 divided by 1 is just 13. And so we get the same answer. And for our diameter, we'll do the exact same thing. We'll put the diameter effort divided by the diameter resistance. So solving for our diameter, we would say our IMA is equal to our diameter effort divided by our diameter resistance, and that is 26 inches divided by 2 inches, and hopefully by now you see that it works the same way. 26 divided by 2 is simply 13. And so the point is, it doesn't matter which version of the numbers you are given. You could be given a diameter, you could be given a radius, or you could even be given the circumference. And if you want, you could calculate out the circumference. Although it's not necessary, you will get the same IMA no matter what. Assuming, of course, if you use the circumference of the effort, you use the circumference of the resistance. If you use the diameter of the effort, you use the diameter of the resistance. You cannot mix and match. You won't get the same answer. But as long as you are using consistent measurements, you will get the same mechanical advantage whether you are using the circumference, the radius, or the diameter.